This is the final installment of a series of videos that will cover decision trees. In this video, we will finish the implementation of a regression decision tree in Python from scratch. Hi, my name is Michael, and I run a blog called Inside Learning Machines, where I cover topics in data science and machine learning. My aim in this blog is to dive deep into machine learning algorithms and explain how they actually work. You can find a link to my blog in the description below. Now, in parts 1 and 2, we introduced decision trees and began the implementation of the CART algorithm in Python. In part 3, I completed the implementation of a classification decision tree model. If you haven't seen any of those videos yet, I recommend you check them out to have a better understanding for what I will talk about here. I have links to all of those videos in the description below. Now here in part 4, we will complete the model implementation in Python for the regression use case. Afterwards, we will test out this implementation to make sure that it actually works. Now if you stick around to the end of this video, I will also compare our implementation with the out-of-box solution we can get from Scikit-Learn. So now we can start by implementing a new class called DecisionTreeRegressor. Now this class will inherit from DecisionTree, which is the abstract base class that we implemented in part 2 of this series. Now if you remember, this abstract class has 2 undefined methods to it, and those define the impurity and how the leaf node is calculated. So what we need to do here in this class is to flesh out how those functions will actually operate. So let's first start by defining an initialization function. So this just takes in the hyperparameters for the class. This defines the max depth, the minimum samples split, and then our possible loss functions. Now in this case, the loss function will be either a mean squared error or mean absolute error loss function. You can of course define any suitable loss function that you'd like if you go in and dig in the code yourself. So here, the first 2 private functions we have here define the possible loss functions that I have included in this implementation. So the first, as I mentioned already, is the mean squared error. So if we go back to the slides that I shared in part 1 of this series, we see some equations here for the loss function. So what this function is implementing is this function right here, just for the mean squared error. And then we also have a similar function, but now for the mean absolute error. And that's defining the function at the bottom of the slide here. So in terms of comparing these 2 loss functions, in general, the mean squared error tends to be more sensitive to outliers. The mean absolute error is more robust against outliers, and it's also somewhat more interpretable of a loss function when compared to the mean squared error. So now that we have our loss functions defined, we can implement our impurity function. So that is just right here. And so now we just take in as an argument the data that has arrived at the node. That's in this form of an array D. So if we select the mean squared error, we will calculate the impurity based on the mean squared error function. Alternatively, if we select the mean absolute error, we're going to compute our impurity based on the mean absolute error function. And then we just return that impurity. The final function in our implementation just determines how we're going to compute the values at our leaf nodes. And so here, like before, we take in the data that is passed into this node. And then the leaf node will just be the mean of the labels that are attached to this array. So it's just the final column here. And we just compute the mean, and that is our leaf node. You can imagine that there's other different ways of computing a leaf node in this case. You can try using a median or some other averaging technique that would suit you if you want to compute a weighted average of sorts. Again, if you want to experiment with this code, you can always look at my GitHub, download this Jupyter notebook, and play around with it. So now that pretty much completes the implementation of the regression decision tree. So now let's test it out. So first thing, let's just run this cell. Okay, so now we are ready to test out our decision tree regressor. So the first thing we're going to need to do is create some data. And so what I'm going to be using here is the make regression function that's available from Scikit-Learn. Using this function, we can just create a simple toy data set that is suitable for testing out this implementation. So what I'm going to do is create a data set that consists of 1,000 samples, has 8 features, of which only 5 are informative. We're going to have a single target. And I've also included a little bit of noise, and I'm setting the random state just so that the output we get here is deterministic. So let's run this cell. Okay, now we can do a train test split where I'm going to set 30% of our data into the test set. All right, and now we can declare an instance of our implementation. Now in this case, I'm setting the hyperparameters max depth to 5, and I'm going to select the mean absolute error loss function. So let's just run this and train it on the data that we have. Okay, now we can generate some predictions. Okay, and now let's see how it performed. So here we can see 3 different metrics being printed out. I have the root mean squared error, the mean absolute error, and then the R2. Now these values they could be good, they may not be. It ultimately depends on the nature of the data itself. What I'm going to use here, sort of as a benchmark test, is to compare how well our implementation does versus the decision tree regressor we can get from Scikit-Learn. So let's just compare the 2 different implementations. I think it's safe to say that the model available from Scikit-Learn should be implemented correctly. So if we get results that are fairly similar to the model from Scikit-Learn, I would say it's fairly safe to conclude that we're doing okay. So let's go now below and let's just call in the Scikit-Learn model. And now let's just repeat what we were doing before. I'm going to declare an instance. I'm going to set the hyperparameters to be the same. So max depth of 5, and then in the case of the Scikit-Learn model, we have to use this argument criterion and set it to absolute error. And then I'm going to train this instance. So that's done. We can generate some predictions and then measure the results. So if we compare these two, it does look like the Scikit-Learn model performs a little bit better. So here we have a table that summarizes all the different trials that I've executed with different hyperparameter configurations. So our custom implementation has the model custom, whereas the Scikit-Learn is just listed as Scikit-Learn. I've tested out the 2 different impurity metrics that I've included in the implementation, along with 2 different maximum depths. So this isn't by any means exhaustive of the different hyperparameter configurations, but it gives us a sense of how things are doing. So we can see that for a lot of cases, the Scikit-Learn model performs slightly better than our custom implementation, and the degree of the difference depends on which metric you're looking at. On the other hand, the best performing model overall is the model with the impurity metric, the mean absolute error, with a maximum depth of 10. So here we have the lowest root mean squared error, the lowest mean absolute error, and one of the highest R2s. And this is actually coming from our custom implementation. So it kind of goes a bit of a mixed bag. Now there's various reasons why we're seeing these differences. It could be like I mentioned previously, the way that we're computing the leaf nodes. There are perhaps ways of improving that would be worth experimenting with. We can also try to extend this table just with other hyperparameters because here it's quite limited to get a better sense of how the two different implementations compare. But overall, I would say that this result is fairly encouraging. The two different models perform somewhat similarly, so they're not, there isn't a dramatic difference between our custom implementation and the Scikit-Learn model. If you enjoyed this content, please like the video or subscribe to the channel. All of the code presented in this 4-part video series is available on my GitHub. Please see the description below for a link to the repository. If you would like to learn more about decision trees and machine learning in general, please visit my site insidelearningmachines.com. I have included a link to my article on decision trees in the description below. Have a great day and see you in the next video.